A lot of material to cover tonight. But I wanted to start with kind of a fun, lighthearted experiment. Hopefully everybody's up for it. You up for it? Yeah, good. All right. So last week we spent the entire class talking about the steps we go through to solve a problem. These are things you do every day of your life that you may not realize you do. Let's take an example. So y'all are mostly or all college students. Most of you probably have roommates or have had roommates or will have roommates. Let's say your roommate is super really smart and she makes a new robot that's super cool. And the robot it works and it follows commands. But it's instructed by interacting with the human voice, not by written programming. So the robot can understand simple instructions, grab something, turn something, squeeze, punch, lift, all kinds of stuff like that. So, as an example, if I wanted to teach your roommate's robot how to do a jumping jack, I would tell her something like, or tell it, the robot is an it, the roommate is a her, robot, start with your hands at your sides and your feet together. Then jump up and spread your legs until your feet are about 18 inches apart, while you're raising your arms to the side until they're at a 45-degree angle to your shoulders. Reverse the motion to your starting point and repeat 10 times. Visualize that. It might be something like a jumping jack, right? So, now it's your turn. Everybody, open up Notepad or some text editor or whatever and write down how to make a peanut butter and jelly sandwich using detailed instructions that someone could follow and make me a peanut butter and jelly sandwich because, as I said, I'm hungry. So let's take a couple of minutes. I said 10. It won't take 10 minutes, but I'll give you 3 minutes to write down instructions that you could give to your roommate's smart robot to make a peanut butter and jelly sandwich. Hopefully everybody knows what a peanut butter and jelly sandwich is. If you don't, Google it. Peanut butter. And I'm going to pick on random ones of you, so you better write something down. No one knows who I'm going to call on yet.
Not to be funny or anything, but are we just going to assume that all the material to make it is already readily available on the table?
Sure.
Okay.
But going back to last week, that's your input. So that was actually a great question. All right. Let's see. Eeny, meeny, miny, Jordan. Jordan, do you want to read your instructions? Does that mean you don't have a mic? Okay. Drew.
Alright. It's like in the middle of still typing it, but I'll go ahead and start. Grab 2 slices of bread and lay them next to each other on a plate. Open peanut butter jar by grabbing and rotating the lid in a counterclockwise motion until it separates from the jar. And then I basically say the exact same thing, but instead of peanut butter jar, jelly jar. Then holding knife in dominant hand, or if there is no dominant hand, either hand of comfort, left or right, take knife and dip into peanut butter jar. Then with the hand that is not holding the knife, grab the bread, raise it up, and then gently, brush the knife with the peanut butter on it across bread. And then, if not fully covered in peanut butter, stick knife back in peanut butter jar and repeat motion until completely covered with peanut butter. And I don't know, if you're that technique, you can like wash off the knife before putting in the jelly to not like contaminate.
Oh, all good. All right. So based on that, so we want to critique your instructions, or does anyone want to critique those instructions? And this is all in fun. Don't be mean.
No, please be mean. I'll take it.
Mine was pretty similar to Drew's, but I did, when I was taking the lid off, I mentioned using your non-dominant hand to hold the jar so that the top.
Ah, that is a good addition.
True. And now that I think about it, I forgot to say to put the lid down.
Yep. So when I was in like the 2nd or 3rd grade, and there's a reason I remember this, we had a very similar thing in the context of just giving instructions. And it was like, write your name on a piece of paper. And we had to stand in front of class, and somebody did our instructions. And I never told them to put their other hand on the piece of paper to hold it still. And so the piece of paper moved everywhere the pencil did. I was so embarrassed. Because again, 2nd and 3rd grade, like it was like almost crying embarrassed. But anyway.
We had a similar, not really, it wasn't something where you had to like demonstrate, like nobody was like doing your instructions, but we had like an exam in the 5th grade, and like if you read the instructions, it would just say like, just sit in your seat and do nothing.
Right.
But then like there was like a whole list of things like jumping jacks and
Yep.
whatever that you had to do, and like all the kids were like doing the things in
Yep.
the exam, but
Nobody read the instructions. Exactly. It's an old favorite. So I think, did you have anything about pulling the knife out of the peanut butter jar?
I did in mine.
Are
Drew-
you talking about my scenario?
Yeah. Drew, sorry.
I didn't get a chance to actually like type it down, so I'm not sure if I said that specifically, but I know I said like dip knife into peanut butter jar.
I think there was a missing and then pull it out.
Yeah, maybe I did.
Yeah, and that's okay. That's the point. Anybody else want to read an attempt? If it's similar or different? Different will be good too. Jaleel, want to read yours?
Mine was pretty similar up until I guess we get to the jelly, because in my house personally, we buy squeeze jelly.
Yes.
To, like, squeeze it, so I wouldn't have to like dip. So from I guess the peanut butter, I'll start with the jelly. I said grab squeeze brand jelly, I got really technical, so I said rotate in a 90-degree angle over bread and squeeze jelly. Place jelly down. Then I said grab knife at a 45-degree angle. Gently spread jelly across bread. Then I didn't get that technical after this. Place knife down. Grab 2 pieces of bread, and then place 2 pieces of bread together. Set bread down. And then I guess if you want to be a little technical, you can say cut bread if you like your sandwich cut.
Only in triangles.
Yeah,
Yep.
yeah.
Corner to corner.
Yeah, definitely.
Yep. Anybody else have anything or anybody critique?
Something I noticed, well, something I don't know if I haven't noticed. Has anybody said anything about like grabbing the knife by the handle and using the blade to dip it in?
Great point. Or putting your bread together with the condiments on the middle, not the outside. So now, if you could imagine trying to tell a robot to do this, and they do exactly what you say, it's really hard to do this without being assuming they know things, assuming no ambiguity, or making things unambiguous. It's explicit instructions that can't be confused. So I liked the turn things 45 degrees, but what if you pick it up upside down? And 45 degrees that way, 40. So like you always got to have a starting point, then you turn, those kind of things like that starts to matter when we think about how we instruct our computers to do things. And so that's a fun activity I like to keep in mind when being embarrassed from the second grade story, how explicit you have to be with computers, especially if you get into things like robotics where things really they spatially matter, right? You got to start from a known point or get to a known point, then you can start giving operations. So anyway, that's fun. All right, let's do some quick homework review. Does anyone hate me for the homework? Yes, and that is an acceptable answer. Thank you for telling me you hate me. Adam, I already knew you hated me. It's fine. All right. Like I said last week, I honestly did not expect you to finish or come up with the right answer for this homework. Give me a Zoom thumbs up if you want to, if you think you answered the or you got the homework complete. I see one video thumb up. Any in the Zoom reactions? Okay, one there. Am I seeing things? Oh, there's one. Is there a middle finger option you can use to say you didn't get it right? No, there's not. I think there are two ways to do this. I was calling it brute force or like the smart math people. Those of you who, did anybody think they got the brute force answer? Lots of for loops, like drawing out a square like the code I indicated on the assignment starts to. Write the code or pseudocode. I did not expect the right answer, so pseudocode would be a good thing, would be an acceptable thing. The pattern. Jaleel, explain. What do you mean pattern?
Well, basically, it took a lot of like research almost on like the task at hand, because honestly, when you gave it to us, I really didn't know how like they were getting the solution. So I actually had to like research, like a lot of research, and then basically like a couple YouTube videos like showed like patterns within this
Okay.
that was able to actually translate into code.
Okay, cool.
Yeah.
I have a friend at work. Just for full openness, this is a challenge on a website, which has like a couple hundred or 1,000 challenging application things like this, where you can like submit. It's like Project Euler or something like that, where you can submit the answers on there and it tests out different languages and whatnot. A friend of mine found this one. He said this was fun, and so I gave it to y'all last week. And after class, I wrote it. It took me about a half an hour to write it, but I went a very brute force mechanism, and I'll show you the code for it in a second. And then the next day I said, "Hey, friend, look at how smart I am. I got it done." And then he showed me his answer, and it was like 3 lines of code, and I was pissed. I was mad at him, and that's what I call the smart math patterns answer. So let me show you what I did. Visual Studio Code solution. So this was my solution. Just quickly, it's 82 lines of code. Now I did printing. I wanted to print it out because I like visualizing this kind of stuff. So if I run my code, let's do the 5x5. I had to figure out my X and Y coordinates and all that kind of stuff because my brain's slow. But then I printed out the spiral. So 1 in the middle, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, going out like that to draw it out. And then I went corner, diagonal, added those. The other way, added those, skipping the middle. And that's the answer. And so that's what that's what I think is the brute force way of doing it. And so if we look at the code to do that, I start out here with a 2-dimensional list based on my size. So basically, basically I have an X size and a Y size. Since it's square, it's the same thing. So in the end, I have a 2-dimensional array. So when I print that out, and I was confusing myself on which was my X and Y coordinates. So I just put in a dummy X comma Y. So when I run it, you saw that my X0, Y0 is here, X4, Y2 is down here. No, other way around. X, Y. See, I even confused myself. It didn't, but anyway, I got the end result right. So then I started in the middle by getting my integer division to find my middle point. And this is where I think I went overboard. So I went into I'm picturing this as a snake. You ever play the game Snake on whatever, where you got to move around, not hit your tail and stuff? So I pictured it moves this way, then it moves down, then it moves that way, then right, then down, then left and right, up. And I found the pattern there. So it moves once to the right, once down, then twice, 3 times, 4 times. So it's that pattern of incrementing how far you're moving 2 times. So if we look at the code here, I have some things. I have my round move, my times moved. So again, going to the right or east 1 time. I have to do that twice, and I'm going east. So anyway, so I did this to end up getting to my filled graph. And so I've got all this if I'm moving east, then my value of Y moves up. If I move east, then next I'm moving south, that kind of stuff to get that pattern. So that's where I printed out. And then the counting was the easy part, frankly. I start at X is 0. So 0, 0, upper left-hand corner. I get the value of that quadrant, or of that square, and then I increment X. So I go from 0, 0 to 1, 1 to 2, 2, because my X and Y now I'm using in a single variable, X. So then I add those all up, down, going top left to bottom right. And then I have to go top right to bottom left. So I do that here. So I start with, that's 0, 4. So, X is greater than 0 and 4 is greater and Y is less than size. So it's a weird while loop. X starts as a big number, Y starts as a low number. And as long as X isn't the middle, which is starting X variable, then I add to my value. Then I add my left and my right together, and I get my total count. So the 5 square was 101. And I think the homework was what, 501?
Yes.
8, is that million? 1, 2, 3, 1, 2, 83,960,501. So I got there. But it's a super inefficient way of doing that. Did anybody do it like I did? Ish.
I did kind of mine the same way, and I had like directions for like up, down to like fill out. And I started with like an empty matrix of the size that I wanted.
Yep.
And then I kind of filled out those values, but I put nuns at first in all my values.
Yeah.
And
Yep.
then I turned right if I could turn right, and if I couldn't turn right, like by turning right I mean like following that path. If I couldn't turn right, then I would continue the same direction that I was already going.
So something like, well, yeah. So empty matrix, then filled out. So yeah, it's the same kind of. That's what I would call the brute force approach. If you did that, it probably took you a while to do. And so when I show you this next code, you're going to say, what the hell? Why didn't I do that? And that's what I said when I saw this code. So here's a pattern that someone figured out. Setting the values in the array of just a simple list based on the range of the numbers. If it was a even number, skipping it. If it's an even number, range 1 through x, x is our size. If y mod 2 is 0, then okay. So yeah, even numbers. Then going through those, this is the magic part of math. Oh, if you want to explain it, you're welcome to.
Can you guys hear me?
Yep.
So basically, I just wrote down the numbers in a row for, let's say, 3, 5, and 7. Those were my test cases that I worked with. And the numbers in a row for, let's say, 3 would be 1, 3, 5, 7, 9. And for 5, it would be 1, 3, 5, 7, 9. And then 13, 17, 21, and 25. So basically, you can just see how much they add with each increment. So for 3, you just add plus 2 4 times. And for 5, you add plus 2 4 times. And then you add plus 4 4 times. So you basically just add. So the reason why I did that list of like even numbers is to make a list of all the even numbers up until the x, which is our 5 or 7 or 501. So let's say if our input is 7, it makes a list that says 2, 4, and 6. And so it knows how much to add 4 times each time, basically.
Okay. So that's the item value, because you're adding that 4 times. So that's somebody who can find a pattern in that I didn't find. So good job.
Mine was a little different.
What was yours?
So basically, I realized that the beginning number is always 1, and the last number is always the size to the power of 2. So I knew what my beginning and end would be. And I also realized that all the numbers on the diagonals were always odd for some reason. And this is all like I learned through the video. Basically, he was explaining it, and it was like it was the easiest pattern I felt that I could translate to code. I made a list of just solely odd numbers, and basically he started writing it out in the pattern was basically after every 4 numbers you would end up having to skip an odd number. So you get 4 numbers, add them, then you would have to start skipping. So like basically you just had to skip an index.
So in this case, 3, 5, 7, 9. Then I skip 11, and I go to 13.
5. And then after 1, 3, 5, and 7, that's when you begin to skip an odd number, basically. And then, so I basically made it a while loop with a nested for loop, and the for loop iterated 4 times, and then I would increment a skipper, basically. So then you start skipping 2 numbers, and then after 4 more iterations, you would skip 3 numbers, and that was the pattern, and that seemed the easiest to translate into code. Because a lot of them were just like equations and stuff like that, and I was like, every time I tried to do it the equation way, I couldn't get the right number. So it just seemed like the easiest way to do it.
So I'd say that is the same logic written a different way.
Yeah.
So this goes back to programming. It's not always the same not always the same approach to get the same answer. So I think with this example, with my example, that's 3 different ways of getting the same answer. And now I feel stupid because mine was by far the most complicated way of doing it.
I have a question.
Yes.
Did you have to start from the middle, or could you start from the outside? But you can just go line by line. Like if you go back to the numbers, you see you add the first, and the top one, top left, and the top right. And then the second line, you move over 1, you add a 7 to 9, and that just goes in the opposite direction. And then you just go down to the middle.
Yep.
And you spread back out.
Yeah, that's again a different way of accomplishing the same thing, and that's actually more efficient than what I did too. Yep. Super cool. All right, let's go to tonight's super fun material. Let's talk about a couple data structures, which we've hinted at, but I want to get a little more formal on them. And so lists we are familiar with, right? Everybody, I think that was lesson 1. We talked about Python lists and how they're a collection of data, linear data in order, all that stuff that matters. So rehashing, we have a list. We can create an empty list with the 2 brackets, the square brackets, and then we can append numbers. And in this case, I'm going to iterate and print them out. I'm not going to run that code because everybody, can you visualize what that code would print out? By now, I hope so. I really hope so. 1, 2, foo. Perfect. 1, 2, foo. Okay, so a queue. This is the standing in line to purchase a movie ticket, or get on a roller coaster. Typical queuing that people do all over the place. And so the idea, the magic words here are first in, first out. So the first thing in is the first thing we take out when we deal with a data structure like this. So imagine the system I work on at work, we send emails. We send billions of emails every year. It's all queue-based because the first person that requests me to send an email, I'm going to send their email first. Then I will send the next person that requested I send an email. Even if they're requesting faster than I can send them, I'm still going to respect the order in which they came in. So that's a first in, first out queue. And if we use a list data structure in Python, we can make a queue by using the keyword append to add the new elements. So if you think visually, the beginning of the list is on your left, the end of the list is on your right. When you append things, you add more things to the right. So the first thing you added is furthest left. So to get the furthest left thing, you pop it from the left. You get it out of the list on the left. Visualize it? Okay. There's a better data structure in Python to do this. It's called a deck. I was going to say a DQ, but it's called a deck, a double-ended queue, and it's in the collections package. So when we write our Python, we write from collections, import deck. We create the object, And then again, we can append data into it, and then we can pop it from the left. There's a reason this is much faster, but we don't have to worry about that all that much. But if you are writing Python and you are making this queue concept of first in, first out, we have this deck object or deck class to make that faster than using a standard list. But either way works. First in, first out's the magic. Got me? Cool. Now we have a stack. So a stack is the first in, last out. Or the last in, first out. Either way you want to say it works. I love the coins in the car coin slot holder, which nobody has anymore really. You know, you put in a coin, push it down, you put in the next coin, you know, rounds in a magazine and a gun, whatever analogy you want to use. Last week we talked about a text editor. So when I'm doing a text editing and I hit Control Z, it removes the last thing I did. Control Z removes the thing before that. That is a stack construct where the operation gets pushed on the stack. I do the next thing, it gets pushed on the stack. I do the next thing, it gets pushed on the stack. When I hit undo, I pop from the stack, the last thing I put in. Unlike every other concept in the world, Python doesn't use the right language, the right words for this, but it's okay. We can still append to our list. Traditionally, you use the word push. We append to the list. In this case, again, left to right. We're appending at the right. And then we pop from the right. So we pop off the latest value that was put into this stack. Cool. Let's talk about complexity. So in computing, we have a concept or a notation called big O notation. And what this represents is the complexity of an algorithm. An algorithm is a set of operations you perform. When we talk about big O, it's specifically meant to be a set of operations on a collection of data. And so the technical words are, we use big O notation to asymptotically bound the growth of a running time to within constant factors above and below. Sometimes we want to bound from above only. I don't know what the hell that means. Asymptotic, so defined that their ratio approaches unity as the independent variables approach a limit or infinity. Cool. So what does that mean? This is how we measure the efficiency of an algorithm on a collection of data in relation to the number of items in the collection. So, again, what does that mean? Let's think about a list. So if we have a list, in this case called my numbers, with 5 values in it, 5 elements in this array or in this list. Let's write a sorting algorithm to sort that data. And let's say that algorithm takes 5 units of time, whether that's seconds, nanoseconds, milliseconds, 12 clock cycles, whatever that unit of time is. So we have 5 elements. It takes 5 units of time. Each element essentially takes 1 unit of time to sort. All right, what if we put 10 items in the array? So if we have twice the number of items, we measure the efficiency of our algorithm based on the units of time or set of operations that get executed dependent on the number of items in the array. So in this case, if 10 elements in our array takes 10 units of time, we have a linear relationship to the number of items in the array. 5 elements is 5 units of time. 10 elements is 10 units of time. Let's assume 20 elements is 20 units of time. That is a linear relationship, right? When one goes up, the other one goes up in a constant value. So in this case, we would call this big O n, where the number of elements in the array or in the collection has a linear relationship to the complexity of the operation or how long it takes. So that's good. A linear relationship is good. It's predictable. It's measurable in a good way, all that good stuff. So, but we can do that very poorly. We can do those sorting. Sorting is always like the example that we'll use when we measure complexity because it's a really easy thing to understand. But this applies to any operation on a set of data. So, what if in this case we had 10 items in our array, but now instead of taking 5 units of time, it takes 15 units. Or instead of taking 10 units of time, it takes 15 units of time or 20 units of time. And then we have 20 items in the array, and it takes 100 units of time. We no longer have a linear relationship. In this case, I don't know the numbers explicitly because it depends on what you're doing, but we can get to the point where we can have a exponential relationship in the amount of time it takes to do an operation compared to the number of elements in your collection. So if this graph were measuring time, our blue line represents a linear growth. Again, straight line, predictable, awesome. The red line represents an exponential growth. It's a very short exponential curve, but you can see it's not a linear relationship. And so the bigger your collection gets, the longer it takes to execute whatever function or set of functions on that collection that you're doing. Anybody have questions on that yet? I know it's abstract so far, kind of. We'll get more detailed. There is a big chart of, I guess, all of the acceptable big O notations. So if we look at this, I'm going to point out a couple that really matter. Excuse me, or a couple I care about. So the first one, O1. That's really, really good. That means no matter how many elements are in my collection, it takes a constant unit of time to perform an operation. I can have 17 million things in my collection and it takes 1 unit of time. I can have 2 elements in my collection and it takes 1 unit of time. That's really, really good. That doesn't happen with things like sorting, but if you have a collection in Python, if we have a map like a dictionary or we have an array, getting an item out of the array by index number, as an example, is 1 unit of time. If my array is 17 million items long, I can use my index notation with the number 3 in it to get the third item. Always 1 unit of time. Log n is a logarithmic relationship. On is linear, like we talked about. N squared is a quadratic or exponential relationship. And then it can get worse. On factorial, like these algorithms to perform functions can be written very poorly, or they can be just very hard algorithms. So what they do is give a bunch of good examples of what they mean. So like the traveling salesman problem is a brute force search, finding permutations on all the data. Traveling salesman, where do I go, when do I go, all that kind of stuff. So figuring that out, you kind of have to just play through every combination of data to figure out the best approach. O log n is adding 2 n-bit integers by ripple carry, whatever that means, and squared. So here we're going to start talking about these tonight, and this is what I want to point out. So going back to sorting algorithms, given a list, we want to put them in the right order. There are different ways we can do that. We can do what's called a bubble sort, a selection sort, and those are both n squared. So it is that quadratic relationship. We're gonna walk through code for 3 of these searches. Let me see if I can find my merge sort here, the one above it, n log n. I forget what logarithmic relationships mean, but I know it's better than n squared. So that's a good thing. So if we're going to be sorting data, our bubble sort and our selection sort is that quadratic relationship. So the bigger our collection gets, the longer it takes. Now that's the same for n log n, but it's not as bad of as a slope. It's a much lower slope. So you can find more information here if you want. On quizzes and stuff that are going to be fun, I'm not going to ask you about log n to the c, whatever the heck these are, where c is greater than 1, polyalgorithmic. I'll talk about 1, n log n, the ones we talked about in class tonight with the examples. All right, so let's do some sorting. I find that I have a YouTube video for each of these sorts. The video is really helpful to show what it's doing visually before we look at the code. I used to do it the other way around, look at the code and then watch the video. I think it's much better to watch the video and then look at the code. So let's try that out. Can y'all see this okay? I'll pause it, or I'll replay it like 12 times just so we can really see it. All right, so here we're starting with our list. 5, 1, 4, 2, 8, 9. I want to play it through the first time. This is a bubble sort. So starting at the left, we look for the highest number between that pair and move it to the right. Look at this pair, move it to the right. Look at this pair, move the bigger number to the right. Look at this pair, move the bigger number to the right. Look at this pair, move the bigger number to the right. So now I know, after one pass, my biggest number is on the right. Because I've looked at every pair, and if the number was, I took the bigger number of the two and made sure it was on the right. Like, I love left-right. It just makes things better in my head. If we were talking about array indexes, the array index 0 would represent the 1 value. So you see they have a limit value of j up here. I had to bubble sort from the left the whole way to the right. Right being length of array minus 1 index. Now I don't have to do the whole way up to the top again because I know that's the biggest number. I'm going to move my limit to the left one. So I'm going to subtract 1 from my limit. So I go back over here. If you saw the bar move, do the same thing. Sort, sort, sort until my biggest number is on the right. Move back, move my limit, do it again. Visually, did that make sense? Is anyone super confused about how that just worked? Or visually why that just worked? That's what I should say, why that worked. All right, so I'm going to play and try to narrate at the same time. Yes, code. Don't look at that code. Their code's awful. Visually, yes, that's what I'm looking for. Starting from the so limit is how far to the right are we going? So my limit is the far right at the beginning. I start my pair, I look and I find and I flip, because in this case I'm going to flip again. I'm going to flip again because my lower number is left. Don't have to flip here, don't have to flip here. Start over and move my limit down 1. Flip, no flip, no flip, limit down 1. Limit down 1. So as far as efficiency goes, we can improve this algorithm, but it still doesn't fix our worst case scenario. So worst case scenario, if it started in reverse numerical order, we would have to flip every single time. In this case, the one pass where you don't flip anything, you can be done. But that's just an improvement on the algorithm, but it doesn't fix the complexity because worst case scenario, it's still that exponential relationship. So let's look at some code for that. I'm just going to open all my code in here. Whoops, that's last week's. Go away. Oh, that's where my homework was. Anyway, code here. All right, so let's look at the bubble sort. So what I did in, come back here, this code, I have a bubble function, and I'm making a copy of my inbound array because I don't want to change my inbound array. This is, we can either affect the incoming array, or we can affect an outgoing array, whatever, doesn't really matter. In this case, I decided to copy the array. So after this line of code, my inbound array and my outbound array will look the same, but I'll have two different arrays. So my limit, the dotted line on the right, I'm starting at the length of my outbound array. If there's 5 elements in the array, the value will be 5. So I'm going to be bubbling up to 1 less than 5. And this is how we do that. So my first pass, notice I have a double for loop. That's what makes it a quadratic relationship. My outer loop is for I in range n. So I'm going to start at 0 up to 1 minus the length of the array. My inner loop, so every time I do that, my inner loop is going to count from 0 to the length of the array minus I. That's moving, that's the one that's really moving that limit, minus 1, because I don't want to overflow my index. If outbound j, so it starts at 0, is greater than outbound j plus 1, the one to the right of it, flip them. Python's cool because I can do that on one line of code. I'm setting what was in j1, j plus 1, into j, and what was in j to j plus 1. That's how I'm flipping them. But only if they're out of order. If it's not out of order, I don't do anything. And then j gets incremented one more time until it gets to be less than the limit. When I go through my first pass, then I increases, therefore decreasing my limit, because I'm subtracting I, and I bubble up again. So this is the code to do it. So if I run this code, hopefully that works. I just created random numbers. So I used the random package, rand_int function, to get random numbers between 0 and 1,000. You'll see my starting array, 321, 300, 700, 800, etc. But when I'm done, they're in order. I think this is the tricky line. This is really the line of code that does the bubble sort. I mean, it all needs to be there, but this is the, let's move that limit from the right to the left, but we start counting at the left, or start sorting at the left with the range, the starting at 0 index. Yeah. Any questions on that one? Why do you do -1 in the range? Great question. So n is the length of the array. So let's say I have a array of length 1, 2, that many items in it. What's the length of that array? What is the length of the array? Sorry, did you say 4? Yes, 4 is the right answer. What is the lowest index? Meaning, if I wanted to get the value 1 out of there, what index would I use? 0. What is my highest index? 3.
3.
So if I tried to act, so my first time looping, I is 0. Length minus 0 is 5. So if I tried to access the 5th, or if I tried to use an index of 5, sorry, let me say that again. Length is 4, I is 0. If I subtract 1 from 4, I get 4. If I try to use index 4, what happens? It breaks. There's nothing at the 4th index. The 4th index is out of bounds. So to get the end of my collection, it's 1, the length minus 1.
Can you explain that again? I got confused.
Yep. So I will show you in code, because I like showing in code. So I have a temp array equals 1, 2, 3, 4. Print test array index 0. First, let's print the length. Length of test array. Save, then play. Oops, I can't do a return. What? All right, let's do that again. Clear. Save, play. Length is 4. And the 0th index, the first item, is 1. To get the last index, print test array. I'm spacing just to prove a point. I can, if I want to get the last index, length of test array minus 1. So this should print out. Whoops, what did I do wrong? There. Length, that. Oh, unexpected indent. I didn't like that. The last item is 4. If I try to print the index of using index 4, because that's the length of my array, I'll get an error. List index out of range. I wonder if this might be easier to see. A, B, C, D. There we go. My 0th element is A. My length minus 1 element is D. And then my length element, the value of length, which is 4. So the 4th element, the 4th indexed element, doesn't exist. So I get an error. So that's why when we're doing a bounds on this for loop, because we're using the J is going to become an index. Actually, really, J plus 1 becomes the index. So now we have to remove the, that's why the minus 1 is there.
Yeah, you switching to letters helped versus the numbers. Because when you said 4 minus 1 is 4, I got confused.
Yeah.
But now I understand the difference between the index and the subtraction.
I'll leave that there. All right. So now it should just, do our list again. So that's a bubble sort. So the way they show it over here, they make it more confusing, I think, because we have a whole bunch of different variables. So I don't know if this is a language, what language this is, but the incoming array of integers is called ARR. A second parameter is the length of that array. So n equals the length of that array. So then we have two variables, I and j. It's just a language that you have to declare variables in. for I is less, starting I equals 0, while I is less than n minus 1, I plus plus, increment I. The embedded for loop, j equals 0, j is less than n minus I minus 1, j plus plus. Our loop in Python, our for loop in Python does the same thing behind the scenes, where it's incrementing the value of I. And then, so if array j is greater than array j plus 1, then swap them. So this is not Python, so you don't have to understand this. That's why I translated it to Python. So that's a bubble sort. So if you later feel like watching that video again, looking at the code again, it'll be there for you. There's a whole Wikipedia article on the bubble sort. But if you ever try to read Wikipedia articles on algorithms, it can be kind of frustrating. So they have a pseudocode implementation here. I guess pseudocode in this case is an official language. But what's good, excuse me, in this algorithm, they show you the steps. So the first pass swaps here, swaps here, swaps here. It works through and does all the swapping. Going to the big O. So if you've ever seen this, when we talk about big O complexity, we talk about worst case performance, n squared, logarithmic, quadratic or exponential relationship. Best case performance is ON. If you write the code right after that first pass and you don't have to sort anything, it only has to go through the array once, which is n, ON. Average performance is a quadratic relationship. Oh, they even have a little GIF of it. All right, so that's our bubble sort. And we've already looked over the code. This is the code on the slides, same code. So we have another n squared sorting algorithm called a selection sort. So let's go to that video. What a selection sort does, there we go. An array is considered in two parts, unsorted and sorted. Initially, the whole array is unsorted. Selection 1, select the lowest element in the remaining array and move it to the starting position. Change the counter for unsorted array by 1. So here we'll start with the kind of the limit like we did before. But here we're starting with it at 0. So meaning anything to the left of 0, which is nothing, there's nothing to the left of 0, is considered sorted. The stuff to the right of the 0 is considered unsorted. Got that? I'll assume yes. So the thing we do is we look through our array to find the smallest number. So I'm looking and I'm keeping track of the smallest number. Aha, found it. It's 11. Let's swap that and the lowest unsorted index. So the lowest unsorted index had the value of 64. The lowest number was 11. Wherever 11 was, I'm going to swap them. Then I'm going to move my sorted array up 1. So now I can consider my array to the left of the dots is sorted. So I'm going to do it again. Now I'm going to find my next lowest number. Which was 12, and swap it with my lowest index. And then I'm going to increment my sorted array counter. And I do that until I'm done. Done. Got it? Visually. We'll look at the code in a second. Anybody confused on how that worked? Need to watch it again. All right, let's look at some code for it. I'll go to Visual Studio again. Where's my selection sort? All right, here's my selection sort because I'm selecting my lowest number. So my main function, again, I'm starting with 20 random integers, and I go into my selection sort. So for I in range length of outbound is the length of the array. Range gives me inclusive on the left, so starting at 0 to be length minus 1. My minimum index, so the picture or the video on YouTube, it showed you finding the lowest value, right? Yes is the right answer. When we move to code, we have to know the lowest value. But how we do that in our variables is we keep track of the index number with the lowest value. So the index number in the array. So minimum index number, we'll start it at I. So my first loop through this outer for loop, it starts at 0. That's my left index. That's my line. That is here. Min index in my code is 0 because nothing's sorted. So while nothing is sorted, I is 0. My minimum index, we'll set it to I. We'll say, okay, the only data I know so far is the lowest index, so we'll see what its value is. We'll assume it's the lowest for now. Then our other for loop is the range I. I is my leftmost boundary plus 1. So the very first iteration, I starts out at 1. I'm sorry, I starts at 0 and J starts at 1. Up until the length of the array. The length of the array always is constant. So we're always going to go up, our rightmost index never changes. It's always the outermost thing. If outbound min index, the thing I think is the lowest so far, if it's greater than J, J is my move to the right on the list. If my min index is greater than J, I'm resetting my min index to my new J, because J is outbound J is less than outbound min index. And we're looking for the minimum index. So we're comparing the two values in the array, but we're storing the index number. So we do that the whole way through, and that min index value only changes, the min index value only changes if the value in the array was lower than the last lowest. Yeah, that's the way to say it. And then when I'm done, I know I have found the lowest number, and I've stored that in min index. So I'm going to swap my first element, the leftmost, with the min index. And since I'm done my for loop, I increments to 1. I've moved my sorted boundary to the right one. I look for my next lowest, find it, and swap. I becomes 2. I look for my next lowest, swap, I becomes 3, etc. Does anyone question this code or think it's too complex or just don't understand it? So I is just counting through the index, correct. In this video, I represents the boundary of sorted and unsorted. So it starts at 0, becomes 1. J represents the movement of the thing underneath the index. So I is the boundary, J is the thing underneath, looking for the lowest number. Do they put up code? I think this, so they put up code here. I think they use the same. Yeah, I, J, min index. Outer loop is I. Inner loop is J. Min index starts at I. I really need y'all to understand this before we move on. If you have any doubts about it, please let me know.
What is outbound and inbound again? Sorry.
Outbound is just my arrays.
Okay.
So in my main function, I create an array called myList. I add my 20 random integers, and I pass it to my selection function as a mandatory parameter called inbound. So inbound is my original unordered, unsorted list. I copy it into an array called outbound, and that's the one I'm sorting.
Oh, okay.
So at the end of this function, inbound and outbound will be different. But after line 4, they're the same. They look the same.
Gotcha. Okay, thanks.
Awkward silence. All right, let's assume everyone gets it. So from the big O notation, there's a chart, the merge sort. This one's fun, but to get there, I have to teach you something new. Has anyone heard the term recursion? I got one yes. Was it a topic covered in Info 350? Or do you just know the term? Either way, whatever, doesn't matter really, just curious. So the recursion is the process of defining something in terms of itself, a circular definition. An example, a circle is defined as something circular in shape. In programming, recursion, I didn't update that one to say not just Python. Recursion is the process of a function calling itself. So a function that calls itself is said to be a recursive function. Now, it may not directly call itself. It may call itself through another function. But still, if the function calls itself, it is a recursive function. So let's go through some examples of what a recursive function can be. So if we talk about the factorial of a number, the factorial of a number is the product of all the whole numbers between 1 and n. The factorial of a number n is the product of all the whole numbers between 1 and n. So for factorial 4, the whole numbers between 1 and 4, 1, 2, and 3, multiply them together, the product, that's the factorial. So in this case, it's 24. Everybody with me? Cool. 2 yeses that time. Sweet. All right, so that's a factorial. So how can we code that? There are a couple of ways we can code it. And the first way I'm going to call the iterative implementation. I think it's better to look at code over here. So factorial. So here's my iterative factorial function. So let's say I'm going to call my factorial function in a formatted string, because formatted strings are awesome, for x. For x in range 20, I'm going to call factorial 20 times. So to figure out the factorial, I'm going to start at 1. And for every number starting at 1 up to and including my incoming n, I'm going to multiply, I'm going to get the product of those numbers. So since this is a exclusive range function, if n is 5, the max, if I just used range 1 comma 5, I would get 1, 2, 3, and 4. But I need that 5, so I'm adding 1 to n in my range function to get 1, 2, 3, 4, and 5. And then I just start multiplying an answer and returning an answer. So when I run this, oops, I need to start at 1. When I run this, factorial of 1 is 1, 2 is 2, 3 is 6, 4 is 24, etc. The whole way down to 19. Factorial 19 is that number. Because 19 times 18 times 17 times 16 dot 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 times 2 times 1 is a really big number. And that's the really big number. Easy. Make sense? I have 1 yes. 2 yeses maybe. Do we want to include 20? I could. 20 plus 1, 21. Factorial 20 is that number. It's just an example. Cool. So that is what the iterative implementation is. Just I'm iterating over the range of numbers that I need to iterate over and multiplying them all together, storing it in a variable. So now let's look at a recursive implementation of factorial. I have a recursive factorial function. So here, this is where you got to start visualizing stuff. The only way I can understand recursive relationships is if I visualize it in my head. So for x in range 21. So again, I'm doing the same outer call. I still want the recursive. I want the factorial of whatever number I want. So just showing you when I play it. Whoops, what did I do wrong? Where's my x not defined? Oh, I think I was highlighting something. There we go. So my output is the same. But the way I get it is very, very different. So I have a function called recursive factorial. Takes in an n. N is an integer, right? Error checking if n is less than or equal to 0, raise an exception because you can't really do that. If n is 1, I return 1. Return n. Remember that. Because the next line, my answer is recursive factorial n minus 1 times n. So let's imagine I'm calling print recursive. I can walk through this visually. Fact 4. output is 24 like I expected. So my first call to recursive factorial, n is 4. Okay? N is not 1, so I'm not returning 1. N is still 4. Now I'm calling recursive factorial n minus 1. What is n minus 1? Three. Very good job. So that means I've called recursive factorial again with 3. N doesn't equal 1. This is a different execution of recursive factorial. We're not forgetting about the old one, but we have a new one. So 4 called with 3. 3 calls with 2 because n didn't equal 1 yet. 2 calls with 1. 1 gets returned. So the top of this stack, recursive factorial ends up with 1. We're returning 1. If we think about the return value of that function as 1, when we called it, the value of n was 2. So 1 times 2 is 2, and I return 2. So remember we talked about the stack data structure? This is a stack. So think about the leftmost being the bottom. My coin example. So the first time I call a recursive function, I call it with a parameter of 4. And the return value, well, I don't know the return value yet. Because I called it again up my stack with 3. I don't know the return value yet because I called it again with 2. Because every time I'm recursing with 1 less than n minus 1. Don't know the return value of that because I then called recursive n is 1. So do I know the return value of n is 1? Yes, we do. I'm going to do this slightly differently because I think I'm still missing something for some of y'all. All right, I start calling it with n is 4. The return value is n times recursive, right? N, I'm looking backwards, n times the recursive. So I'm writing it a little backwards up here. I could write it the same way to make my example line up. N times recursive. So n times recursive. Well, we know n is 4. We don't know the recursive yet. So up here, n is 3. Because I'm calling it's another function. It's a different execution of the function. So it's different variables and all that kind of stuff. They're named the same, but they have different values. So I know the return value is going to be 3 times recursive. Recursive is 2, and the return value is 2 times recursive. When I finally get to n is 1, my return value is 1. Okay? So if my return value is 1 here, I know that's the return value for my recursive function here. 1 times 2 is what? 2. So that return value of this layer from the one above it now we know is 2. 2 times 3, my new return value, is 6. 6 times 4, my ultimate return value is 24. Anybody's brain pop? Okay, we got one got lost, 2 got lost, and that's fine. We'll do this. I have another idea on how to do this. I understand it, then lose it, then understand it, then lose it. Totally get it. Let's try a different visual.
Again, idea is
Say again?
that like the idea kind of makes sense. Just go through it.
Yep. Let's give a label to every time I call the recursive function. So the first time I call the recursive function, I'm going to call it R1. Okay, cool. R1, the first time I call recursion, n equals 4. So we could almost say R1.n equals 4. But when programs like this define a variable, it's always in the scope. It's always in a scope. So in this example, n is only valid in the scope of the recursive fact function. Like, I can't reference n down here. There's no n in this scope. N is only available in this function. So when I call the function, the variable is defined within Python or within whatever programming language you're in. It's defined by function within that function. So by the function recursive fact, by the call of recursive fact function, there is the concept of n. So the first time I call it, I'm going to call it recursive fact 1. RF1, recursive fact 1. The first time I'm calling it, I'm passing in n is 4. This is my little shortcut way of saying, and my return value is going to be n times something. So 4, right, n times something. Something is another call to recursive factorial. So I'm going to call it recursive factorial 2, but I'm passing in the value of 3. So in recursive factorial 2, n equals 3, and my return value is going to be 3 times recursive factorial 3, passing in n minus 1, which is 2. With me so far? So when I call recursive factorial the third time, n equals 2. So I'm taking the value here and moving it up. Taking the value from here and moving it up into the new call. This is a stack. I'm building up a stack. Never forgetting what's below it. So now I have n is 2 times, well, I got to call it again, recursive factorial 4 with the value of 1. Recursive 4, n equals 1. What is my return value? If n equals 1, return n, which is 1. So I know my return value is 1. So now imagine we are doing algebra in the 8th or 9th grade, whatever grade you did algebra in, 10th grade, whatever grade, 6th grade, I don't care. RF4 can be a variable. It really is a variable, almost. So RF4 is equivalent to 1. So let's say that's equivalent to 2 times 1. 2 times RF4 is the same thing as 2 times 1, because RF4 is 1. So now we can say that equals 2. So now we can say RF3 equals 2. So 3 times RF3 is the same thing as 3 times 2. 6. All I'm doing is filling out these variables down the stack. Now I'm popping the things off the top, forgetting about them once I get their return values. So now I know RF2 is equivalent to 6. So I can rewrite this one and say 4 times 6 equals 24. RF1 equals 24. 24. That's my answer. So you see why I have to visualize it in my head. Because the one condition is dependent on the next. And that's all we're drawing here is the one condition, RF3, is dependent on the next, RF4. And so the important parts here is, how do I change n, or whatever my value is, going into my recursive function? And then when do I end my recursive function? So we broke that down pretty well, I think. But this is the important part that I was just touching on. It is critical in a recursive function to always have an exit point, or figure out when you're done, when you stop recursing. Otherwise, you'll hit an infinite loop and you'll blow your stack. Stack meaning the data structure. Because looking at the code, our CPU has to remember this, 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 this. If we did factorial 20, it would be remembering 20 calls in the stack. So it has to keep that in memory. The CPU has to have access to it. What happens if you have an infinite loop? You'll run out of CPU and memory. You'll blow your stack. And let me show you what that looks like, because it's fun. So let's say I take out my end function. Meaning, and I'm going to take out my error check as well, because I want this thing to just go n minus 1 forever. I'm going to play it. Oh, what did I do? Oh, this is not code. This is not code. Okay, cool. Let's clear that. Run that. Hit save. Then run that. I got an error saying previous line repeated 996 more times. Recursion error. Maximum recursion depth exceeded. I blew my stack. So you always, 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 always need an exit point. My exit point where I don't recurse anymore is when n equals 1. No, it's not. There we go. And another way of doing this, if you're curious what happens, print n. 4, 3, 2, 1, 24. I called factorial with 4, then it called itself with 3, 2, and then 1, and then it was done. Any questions on that? This is one of the hardest concepts for some people to get in software development, in coding. So if we have to spend another half an hour going over it, more than welcome, more than happy to. I just got to think of better ways to go over it. Good. So you get the stack part now? How you pop it out until you're done? Coming back down the stack? I always think of it as like rolling back. You know, you build something up, then you roll it down. You just roll back down your stack. It's like a mountain. Cool. All right, so the reason we did that. Let's talk about merge sort. Based on that recursive lesson, what kind of function do you think a merge sort function is? Think it's a recursive function? Yeah, it's kind of a recursive function. So let's watch the video. I love these videos. Thank you, Geeks for Geeks. Merge sort is a divide and conquer algorithm. It divides your input array into halves, and then it calls itself for the two halves, and then merges the two sorted halves. So, before we get into this, visualizing it, factorial had one recursive stack. This one, we're going to start with one stack on the bottom. Then we're going to split that into two things, and we're going to have two calls from there. Each of those is going to split into two things. Each of those is going to... So now we're kind of building this reverse upside down tree. It's fun. The merge function is used for merging the two halves. The merge sort function recursively calls itself to divide the array till size becomes 1. So the exit point, the terminal point of this recursion, is when the array becomes 1 element big, long, one until the array has one element in it. Ignore the code, but we're dividing it into two halves. Divide it into two halves. Okay. So if I didn't count, but I think this is 1, 2, 3, 4 layers deep, but each layer has multiple instances of that function. Like our factorial layers only had one instance of the function. This one divides and conquers. So now, once we get there, we have to merge them together. So these two, so I'm starting to merge these in order. So my last two, if I look on the left side, 38 and 27, those are my last two single size arrays. I'm going to put them together in order. Then on this level, I'm going to find my lowest and put them together, merging these two. So this is me going back up or back down the stack. We're going to watch this again. I'm going to talk through some of this. So we've gotten to an ordered list. Remember the part, the big O notation on this is n log n. Remember that? In computing, whenever you do these branching things, like it's called a tree, whenever you do these trees, the complexity becomes log n. Because now you can only, your operations typically happen now on 1/2 of the data. That's not a great way of saying it, but it's something like that. The n log n, watch when it starts sorting them together. So let's go back a little bit. All right, so we have divided and conquered. We're going to look at 38 and 27. Since each side is sorted, I only have to go through the list once. What's happening is my program is comparing, in this case, which is the lowest value. The leftmost unsorted on the left or the leftmost unsorted on the right. It's called a shuffle sort. So it's taking two lists that are in order and just finding out which of the 0th element is lower. It'll take that one. So between 38 and 27, they're both the 0th element. It takes the 27, puts it first, and then the 38. Here, same thing, 3, then 43. Here it'll take 9 and 82, and then 10. It just brings down 10. It maintains that. Chopping it up recursively and arranging them in the meantime doesn't take a toll on time. Exactly. I mean, it does take time. You saw it's not a linear relationship, but it's not a total quadratic exponential thing. It's a better slope than that. So here, watch the red. If we think about the red as our leftmost index, like we had the dotted lines on the videos beforehand, right? My leftmost index, I have two of them. I have one for my left list and I have one for my right list. Two variables, okay? Leftmost index. So they both start at 0. So if they're both 0, I say, okay, which one is lowest? Okay, my right index number is the lowest number, so I'm going to store that. Then I'm going to increment my right lowest index. Then I'm going to check my left lowest index, 0, to my right lowest index, 1, which is lowest. Bring it down. Increment the one that's... So you'll see it's comparing those, and it brings down to 3, and it moved up the rightmost index. Now it's going to compare the left lowest index to the right lowest index. In this case, it'll take the left lowest index and increment the counter of the left lowest index, which is now 1. So again, it's going to take the 38 and the 43, and it's done. So this is how it's sorting them back together. Over here, left array has 2 elements. Right array has 1 element. Left lowest is 0. Right lowest is 0. It picks my left one, increments my left lowest index to 1. Now it compares left 0 to right 0, left 1 to right 0. Pulls right 0. There is no more right, so it's got to be the one on the left. I know I'm talking through this quickly, but the code is kind of confusing. But once we go through this a couple times, we'll see it in the code and it'll make more sense. All right, so now I have 2. I'm down to my last 2. I have 2 ordered lists. And my left lowest index is 0. If that's mirrored, then that could be confusing. Whatever. My left lowest index is 0. My right lowest index is 0. I found out which one's lowest. It's left, so we'll increment left. Right, now we'll increment right. Right, we'll increment right again. We'll pull left, increment left, left, increment left, left, then take the whatever's left on the right, whatever's remaining on the right, and I have a sorted list. So what this said at the very beginning, this takes 2 functions to do. The merge sort function is what's responsible for chopping the arrays in half and recursing. Then when it's done, it merges them back with the merge function. So let's look at that code. And I really hope my code does the same thing. Merge sort. No, I do it all in one function. We'll be right though. We'll understand it. Consider this top to be the merge sort function. So let's go through this. My main function looks the same. I'm sending my list into my merge sort function. This one I'm not copying it into a second function. I don't know why I didn't, but I didn't have to, or I didn't want to, or I didn't, whatever. Again, I'm calling it inbound. So this is my inbound array. If length is greater than 0, meaning if length is greater than 1. So if length is 1, I'm not going to do this. That's my terminal status. Always find your terminal status. So mid is my integer dividing midpoint to find that middle of my list. I'm assigning to a left array and a right array. So in Python, they're totally doing that visually, not how I would have done it, but that's okay. Half of it and the other half of it is into two arrays. Then I recurse with each of those arrays. So this is where I'm now treeing out multiple times. So once I've treed out to the 0, or to the when my list is only of item 1, then I don't do anything. My inbound array is what it was when I sent it in, or my outbound array is what it was when I sent it in. So here's where I look at my leftmost and my rightmost arrays, like we were doing now in the second half of the video. I is less than left array length, and j is less than right array length. So I is my left index, j is my right index. If my left array I is less than my right array j, then my k is where is it going in the new array. K start at 0, so I'm going to fill in my new array on the left, so 0. So if left array is less than right array, I put k into left array, or take k from left array and put in the original array, increment I. No matter which one was greater than, I'm incrementing k because that's where I'm putting it in the new array. And so I'm running this while loop again. If left array I is less than, and then so this is looking at both sides and constantly pulling out the lowest number and incrementing k. Then see if there's anything left over, because the way this for loop is written is if one of the array lengths is different than the other, it's only going to do this until the lowest number. So let's say left array was length 9, right array was length 8. It would only go up 8. It would only do this until one of the sides was emptied out. And when one of the sides is emptied out, we can then continue I or j to fill them into k, whichever one's remaining. Only one of them would ever be remaining. And so since this was recursive, it takes those two, puts them together, and returns it up. And that was a recursive call. So there's another one coming in from the other side being sorted until it all sorts down below. So that's this second part again. The splitting part's easy. The merge sort part is easy. Find our middle point, integer division here, length of 7, whoops, I was wrong, split it, continue to split it. This is the recursive part over here, where I just call merge sort again with half of the array, and that's where I start sorting. Any questions? It's definitely confusing. I agree. I suggest coming back to this video and this code a couple times this week and seeing if it clicks. Is it faster? Yes, it is faster. The bigger the data set, the faster it'll be, compared to the other sorts. That's what I should say. That divide and conquer. So there are trade-offs. The bubble sort, which was an n squared, big O n squared, that quadratic big steep relationship. It's not a recursive function. So it's CPU heavy. It's processing. It's looking at the same data over and over and over again until it's sorted. But it's always linear, like in one function. Recursive makes it, being recursive makes it a bigger stack, like we talked about the CPU stack. So it's going to use more memory, but less CPU. Yeah, that's right. Less CPU because it's doing the dividing, but more memory because it has to do the stack. Good question. All right, I think that was what I had for the slides. That's what I had for the slides. And I didn't come up with a fun programming assignment for you next week. Tonight. But if I come up with one tomorrow, I'll make an announcement for it. If I don't do it tomorrow, I won't do it. But I'm reserving the right to put out a homework assignment tomorrow by the end of the workday. Because I'm mean. I won't make it like last homework. I'll come up with another merge sort type algorithm. I'll make you write that one. Ooh, 10-page paper on Tuesday. Gross. All right, I'm going to hit stop recording.